I put this image of Mount Rainier up. Now, most people that would look at this photograph would realize that in order for the mountain to cast that shadow on the clouds above it, the sun had to be coming from an angle or an altitude lower than the peak of the mountain.
That's why they call me the fallacy guy. The fallacy guy. Till the day I die. Bob fallacy guy.
Okay, now that's pretty funny, right? But let me get serious for a minute. Logical fallacies are not funny. They mislead people. You jump to conclusions. And this is why, and a guy who calls himself Bob the Science Guy isn't rigorously checking out these phenomenon. He's just naming it and declaring it from a very limited understanding, a very limited point of view. Okay, before I go into more of the visuals of this, let me just show you from that little 17 seconds he spoke about the Mount Rainier and its shadow, he committed a few fallacies right there, a few logical fallacies. So let me dig into those. So I'm going to play a little bit of his speaking, and I'm going to interject and show you more of his fallacies. And that's why they call him Bob the Fallacy Guy.
Now, most people that would look at this photograph,
No, Bob the Science Guy. Real scientists don't take a poll to determine what the cause is of an effect. That's an appeal to consensus fallacy, and it's pseudoscience.
now most people that would look at this photograph would realize
They're not realizing anything, Bob. They're just jumping to a wrong conclusion like you are, and also committing a reification and affirming the consequent logical fallacy.
that in order for the mountain to cast that shadow on the clouds above it,
And then you claim it's casting a shadow on the underside of the clouds, when in fact it looks to me like you see the shadow on the mountain. That's not on the clouds, the narrow part, and then as it spreads out, I don't know that that's on the clouds, but it doesn't matter, even if it is. The point is that the apparent height of the sun is lower than the apparent top of the mountain and will cast a shadow upwards from your perspective or your point of view.
the sun had to be coming from an angle or an altitude lower than the peak of the mountain.
No, it doesn't, Bob. The actual location of the sun does not need to be lower to cast that shadow. The apparent position can be lower and cast that shadow from your perspective. Okay, see that light at the end of the road? That's a street light. That street light is about 30 to 40 feet high. This sign is, let's say, 12 feet high. Okay, I'm sitting here on the road looking at it, and so the shadow goes up from my perspective, even though that street light is higher than that sign, maybe 3 times higher. Because you believe in a spinning ball earth, you're saying that the sun is actually lower and shining up. But you know, Bob, again, that's fallacious reasoning, because the sun on a flat earth will rise and set due to perspective. Okay, now, look at the light poles going off into the distance. You see how they get lower and lower and lower? And that would be the apparent height of the lights. It's the same with the sun. The sun is high up. How are we seeing it on the horizon? For the same reason. So clearly, I can look out at the horizon and have the very last light post shine its light in my eye and cast a shadow on my face. And that shadow is parallel to the ground. I can look at a light that's, when I'm standing under it, is 30 feet over my head, and I have to look straight up to see that light. I can also look at a string of streetlights that go all the way to the horizon, and I can look at the last one, and I can look parallel to the ground, about 6 feet off the ground, and that light is in my eyes. And the shadow it's casting is also parallel to the ground. How's that possible? Right, Bob? But it's all a perspective issue, which you guys don't understand. It's like you put up this picture of Mount Rainier and its shadow. The reason is the apparent position of the sun is lower than the top of the mountain from your perspective. It appears that way, but it's not really. But that's how it appears due to the way things converge, just like these streetlights. That's not curvature. That's not due to the spin of the earth right there, the rotation of the earth. That's convergence, Bob. The streetlights aren't actually shorter streetlights and getting shorter and shorter. They're not actually lower. They're just visually lower, Bob. That's perspective. So the argument we keep having is the earth flat or is the earth a ball? See, that's the argument, but not whether perspective is real. Bob, perspective is real whether you believe it or not. Perspective doesn't care whether you believe in it or not, Bob, or whether you're ignorant of it. It's real, and this is what explains what we see. You cannot prove the ball. We prove the flat Earth pretty overwhelmingly. The Earth is flat. Visually, that's our experience. And the Earth is not moving. So really, the burden of proof is on you. But you guys aren't honest enough to admit that. But the burden of proof is on you. You guys cannot prove a spinning ball. And all of the observations we see show that we're on a flat, immovable, or motionless Earth. Okay, so as these light posts go down, you're not going to call that curvature, right? You're going to call that's definitely perspective. And when I put the perspective lines in, you can see that. See, it's the ball and the flat Earth that we're arguing over, but there's no argument about perspective and perspective convergence. Things will go down the further they are from you, and they will rise the closer they are. Okay, let's go back to the street lights. So I got rid of all those light poles. Now I just isolated the last one. And let's say that's bright enough to shine all the way over here to cast shadow. It'll cast a shadow in my eyes parallel to the ground. And from my perspective, being that the light is lower than this sign, it will cast a shadow upward, Bob. Now, is that street light actually lower than that sign? No, it's actually taller, but its apparent size at that distance is smaller and is casting the shadow upward. And that looks just like your Mount Rainier photo, which you declare is the actual position of the sun, instead of admitting that it could be the apparent position of the sun on a flat plane. See, look, where you're sitting, Bob, the convergence lines would look like this. This is how they would be for you. Does that look familiar? Does that fit what you're looking at? Yeah, it does. You notice that? See the shadow? See the shadow is narrow over here, and then it's wide. That's perspective. So not only is it wider, but it's taller. It's going up. And it appears to be going up, Bob, because the mountain is further away from you than the shadow you're looking at. And the apparent position of the sun is further away from you than the mountain. So the mountain, like the sun, follows the convergence lines down and gets lower and gets smaller. Angular resolution, Bob. Okay, now, before I go on, I know somebody's going to say, oh, then, well, if the mountain shrinks and gets smaller and everything gets smaller, why doesn't the sun get smaller? It should get smaller on a flat Earth. Well, actually, it does get a little smaller. According to all the filtered time-lapse footage I've seen, the sun changes a little from noon. Like here, this is, you have high noon and about 3 p.m., and you can see it's getting a little bit smaller. And then at sunset, it's even smaller. So it's squashed a little bit on the vertical axis, and you can see that then the overall circumference is smaller. And by the way, these pictures are from a Wolfie video. So we can see the sun does shrink a little bit, but why doesn't it shrink a lot, like a train going down the tracks away from you or a car driving away from you? Well, the reason is it's not on your eye line, right? It's moving, the sun is high up and moving parallel to the ground, which essentially makes it move perpendicular to you, right? So that makes all the difference. So here I did a demonstration with some wiffle balls, and I show that I think they're 6 or 7 feet apart, and they're the same size, but when the camera looks at it on the eye line, on its eye line, they look the far one looks way smaller. But when I raise the camera up, right, it's kind of like if the two balls were in the sky moving overhead, then they look about the same size because now they're parallel to the ground or parallel from where the camera is, and they're moving essentially perpendicular to the camera. Okay, I have another couple views that are pretty cool. Let's see what it would look like at the exact time this photo was taken. Let's see what it would look like from on top of the Mount Rainier. And let's see what it would look like right here where we took the photo, but let's go up as high as the top of Mount Rainier. And let's see these two perspectives and see how they look. From the camera's point of view, the sun is lower than the mountain because the sun is maybe just above the horizon. So the horizon would be level with the eyes of the camera. But Bob, if you went up onto the mountain top, where would the horizon be? It would be up to your eye levels on the mountaintop. Eye level. Where would the sun be? It would be above the horizon, right? Right there at sunset. The shadow would be cast straight to downward from your perspective on the mountain. So this is all a perspective issue. So you just jumped to a conclusion and you've misled a lot of people who are watching watched your video and have watched you espouse this as some type of proof. Where it's not proof, Bob. It's a logical fallacy. There are other causes, other explanations, right? So there I showed you what the perspective would be from the mountain. If you were there at the same time this picture was snapped. Okay, so where this picture was taken, let's go up higher. Let's go up, let's bring the camera up to the height of the mountain, to the same elevation, and let's see what happens. So here we go, we're going up. What's happening to the shadow? The shadow's going down, right? And the sun and the horizon are rising with the camera. So in conclusion, Bob, you wouldn't look at these pictures of the lamps going down and you wouldn't call that curvature, would you? Of course not. But when it comes to the sun, you are reifying your spinning ball and saying that that is curvature. But like I said, all the evidence is with us. The Earth is observably flat and observably motionless. And you just got a p-brane perspective lesson, Bob. But you know what? I know you're still not going to get it. And that's what's amazing with you guys. Okay, thank you everybody who's bought a shirt. And someone out there bought multiple shirts. You know who you are. Thank you so much. And if there's a style and color that I don't have, let me know and I'll make it for you. Let me know in the comments. All right. Thanks for tuning in. You can see my t-shirt. It's awesome. I've got some new prints. Go to, there's a link in the description. Go to my online store and check out these new super cool t-shirts. All right. Thanks so much. Talk to you later. Bye. Here comes my dance.
That's why they call me